Kia ora Year 12. This video is the second one about the discriminant in quadratic equations, and this is quite a step up from video number 1 on basic properties of the discriminant. So in this one I want to look at 5 harder examples, and I also want to look carefully at the different language used in questions about the discriminant. So these are the 5 examples that we're going to do, and you'll see that the questions are all ones like this. So when does the function have no real roots? When does the graph have one real solution? When does the equation have one real root? And so on. And then when you look at these equations, you'll see that instead of just having numbers in them, they've all got things like K and Q and, P, Q, R, that sort of thing. So that's what's going to make them a little bit harder. This might run into 2 videos. I think it's worth going through really slowly because these questions are often merit questions that pop up, and sometimes the excellence questions will use these skills as well. So let's first of all start by just going back to what the discriminant is and what it's about. So the discriminant happens in a quadratic equation, or it's a feature of a quadratic equation. We write our quadratic equation like this: ax squared plus bx plus c is equal to 0. And those a, b, and c coefficients do different things to the shape of the graph. So b squared minus 4ac is the discriminant, and we abbreviate it with a little triangle. So there are 3 main different cases. The first one is where we have a parabola and it cuts through the x-axis twice. So that's one example. We might have an upside down parabola. It might be on this side or it might be on this side. The main thing is that in each one of these you can see there are 2 intersection points, 2 x-intercepts. And in all of those cases the discriminant is strictly positive. So that's case 1. Case 2 is the one where the parabola is just touching the x-axis, or it might be an upside down one, in which case it will look like this. Okay, so very bad graphs, but that gives you the idea. In all of these cases, the discriminant is equal to 0. And where that comes from in the quadratic formula, I went through in class and also in video 1. Right, and then the last one is one where we've got no x-intercepts, right? So it doesn't touch or cut through the x-axis. So that's a case like this one, this, or upside down ones down here. And for all of those, we have the discriminant is strictly negative. Okay, so there are no real solutions. So let's look now at the language. So I've made this into a table. Where's the table that I want? Where's it gone? Oh, here it is on this one here. So what I want you to do now is just to read through those quickly and see if you are confident with the discriminant condition for each one. They're all pretty similar, but they're just different ways to ask the same thing. Okay, so here are the different situations. The first one, the graph will not cut through the x-axis, is where we have a negative discriminant. Other ways to ask that same thing are to say, where are there no real roots or no real solutions? The second case is the one where we've got 2 x-intercepts. So in that case, we have 2 distinct real roots. We have a strictly positive discriminant. We use the words solutions and roots pretty much interchangeably, so we can also say where are there 2 distinct real solutions, or sometimes that will just say 2 real solutions, right? And then the last way to say that is the graph will cut through the x-axis. And then the last case is where it just touches the axis. And let me change pen colour. So it will just touch the x-axis, means that the discriminant is 0. That's the same as saying there is exactly 1 real root. Or other ways to say that, 1 real solution. Or now 2 that are a bit different, 1 repeated real root, or 2 identical real solutions or roots. So where that's coming from is from this idea here, that if we've got, for example, y equals x minus 3 squared, most people would think of that as having 1 real root, which is x equals 3. But we could say that that's the same as having x minus 3 times x minus 3, right? So we call that a repeated root or a repeated solution. So let's look now at those 5 questions. And I've put language next to them that is going to make you figure out what our discriminant condition is. So pause the video now and just try to solve these. And they will require quite a bit more work than the ones in video 1. Okay, so I'm going to start with question 1. We've got y is equal to 2x squared minus kx plus 7. So we want to know when it has no real roots. So no real roots means the discriminant must be negative. A is equal to 2, B is equal to negative k, and C is equal to 7, right? So here's A, B, and C. So B squared minus 4AC is equal to negative k squared minus 4 times 2 times 7, and that has to be negative. Cleaning this up gives me k squared minus 56 is less than 0. So this is what we call a quadratic inequality. And to solve that, we can say k squared must be less than 56. But we need to be really, really careful here, because if you think about what that looks like, if we drew a parabola just with k, there's my k squared. That's what it looks like. We want to know when k squared is less than 56. So we could draw 56 on here like this. So which values of k are giving me k squared being less than 56? Well, pretty obviously it's going to be for positive ones that are less than the square root of 56, but we also have these negative values. So we're going to have negative root 56 on this side. So I've deliberately made these questions not having easy numbers because they're typically at least merit questions. But let's look at how we do that with an easier example. So that's my final answer there. Any value of k between negative root 56 and positive root 56. But suppose that I just had k squared is less than 9. Well, then what would I have? K squared less than 9. I'd have k that has to be between negative 3 and positive 3. So there's 9. So what value of k will give me exactly 9? It's 3, or it's negative 3. And so for any value of k between these two numbers, I'll have a k squared less than 9. So that's question 1 done. Okay, let's look now at question 2. Question 2 turns out to be a little bit easier. We don't end up with a quadratic inequality. Sorry about the background noise. That is the new puppy chewing on a shoe, but I'm going to keep on going. Right, so on to question number 2. So question 2 goes like this. We've got 3x squared plus 4x plus q equals 0, and we want to have, when does this graph have one real solution? So one real solution means the discriminant has to be equal to 0. Right, you must write some reasoning for what you're doing with the discriminant. So A is 3, B is 4, and C is Q. Really easy one here because they're all positives. So B squared minus 4AC is equal to 0. That gives us 4 squared minus 4 times 3 times q is equal to 0. Cleaning this up, we get 16 minus 12q equals 0. So we're back to a year 9 equation this time. 16 is equal to 12q. And then we can divide both sides by 12, and we get 16 divided by 12 equals q, and we better simplify that. Now for this one here, we get q is equal to 4/3. Now that's not the same as 1.33. So please do not write that, okay, because we like to leave that as a fraction where we can. In that first question, where we had the square root of 56, because that's an irrational number, it's acceptable to approximate that. So we could, with that one, do this, 7.48 to 2 decimal places. So the reason why we treat those two things a little bit differently is that here 4/3 is a rational number. It's an exact fraction. We don't need to change it to a decimal approximation. So let's not do that. Okay, on to question 3. Right, so this time we're asked, when does this equation have 2 distinct real solutions? So this looks really easy, right? We've got 3x plus 2 times x minus 4. The trouble is it's equal to k, not 0, right? So we know from much earlier in the algebra topic that when we've got an equation like this, we have to expand out this, and then we're going to subtract k from both sides, because the way that we solve quadratics is always to have them equal to 0. Okay, so let's go on with this one. So the first thing to say is, well, we need to have a discriminant condition. So for 2 distinct real roots, we need the discriminant, that little triangle thing, has to be strictly greater than 0. So we've got this equation, 3x plus 2 times x minus 4 is equal to k. 3x squared plus 2x minus 12x minus 8 equals k. 3x squared minus 10x minus 8 minus k equals 0. So watch carefully how I handle this next step, because it's often confused by students doing these harder ones. I need to find my A, my B, and my C, but I'm going to have to use them in my discriminant. So it's much easier if I can go like this. I've got 3x squared, right? So that's going to be A, minus 10x, that's going to be B. But this is all my constant term, right? Minus 8 minus k. So I'm going to take out the negative, so make it minus, and then make it minus 8 plus k, right? So I'm factorizing that out. You'll get used to doing that, but it does feel a little bit weird to start with. But hopefully you'll see that it's going to make things cleaner when I come to my next step. So now we've got A is 3, B is negative 10, and C is negative 8 plus k. And we need to have the discriminant being strictly positive. So B squared minus 4AC is equal to negative 10 squared minus 4 times 3 times negative 8 plus k. There we go. Now expanding that, 100 plus 12 times 8 plus k, and that thing must be strictly positive, right? This is my discriminant. We've still got to clean it up. So we get 100 plus 96 plus 12k is strictly positive. 196 plus 12k is strictly positive. We're just about there, and we are going to use the lovely fraction simplifying button on our calculators. So negative 12k is greater than negative 196. K is greater than negative 196 over 12, right? Which gives me k is greater than negative 49 over 6. Is that right? That's not right, is it? Negative 49 over 3. Let's see. Yep, that's right. Okay, so we can divide by 2 and then divide by 2 again. So that's my final answer here. Okay, so let's just go over a couple of things in this one. I've got 1 minute left. I'm not going to do questions 4 and 5 in this video because I want to make sure I've done these really slowly. Things to notice in here. The first thing to notice is that I expanded this out, but this does not equal 0. So that's why we've got to do a bit more work. Okay, so the work we've got to do is to make sure we're always working with expanded form when we're doing anything with a discriminant. So because this is not an expanded form, it's in just a weird factorized form with something over here that's not 0, we have to change it. So that's what all of the first part of the question is getting it down to there. Thanks for watching. I'll do another video later on with the last 2 questions.